Okay, for this module, we have 3 learning objectives. We're going to do them all at the same time because they run into each other quite nicely, so it's hard to separate them. You have a calculate in each learning objective. Calculate and interpret convexity and describe the convexity adjustment. Calculate the percentage price change of a bond for a specified change in yield, given the bond's duration and convexity. And calculate portfolio duration and convexity and explain the limitations of these measures. Difference down here is we're looking at portfolio duration. So in other words, you have bond 1, bond 2, bond 3, etc., all with different durations and convexities. Well, how do you calculate the portfolio duration? All right, convexity here, modified duration. That is a first order effect, made that clear in the previous reading. It is a linear approximation to the change in the price of a bond for a change in yields. Convexity is a second order effect, and this is for option-free bonds. Once you have optionality, you don't always have the same type of convexity relationship. So have a look at the graph that's drawn, and you can see the curved line. I'll try to draw an overlay here in yellow. You can see that. There is your price yield curve. You can see that it's convex. The straight line here, which I'll try to draw out freehand, is your tangent line. And as you're pricing something out, we know that we have to get our price from the linear approximation, modified duration, to the curved linear line, to the convex line, hence the name convexity. Clever, isn't it? So, the nice thing about convexity is, look what happens to the price yield curve. It tends to flatten out as the yield to maturity increases, but it really spikes as the yield to maturity decreases. So convexity is a good thing. If we expect interest rates to have a high level of volatility, in other words, to change a lot, we would like a portfolio with a lot of convexity because the percentage change in the price of a bond for a drop in yields will be greater than the percentage change in the price of a bond for an increase in yields. That means when yields drop and prices go up, let's say yields drop 200 basis points and or yields increase 200 basis points, the price increase will be greater than the price decrease. That's what we would like when we're holding an asset, is that when it goes up by a lot, but when it goes down, it doesn't go down by as much as it went up. And how do we add the convexity adjustment? Notice the plus sign here. There is adding, right? So the percentage change in the full price of a bond is the very first thing we did, the linear approximation plus the convexity adjustment, which is 1/2 multiplied by annual convexity multiplied by the change in yield squared. Well, the first one is a constant. The second one you will already have because we multiply modified duration by the change in yield for the linear approximation. Annual convexity is the only statistic we have to calculate. You'll recall this was the calculation for approximate modified duration. For approximate convexity, because we can calculate convexity 2 ways. We can calculate it in the spreadsheet way, the way we calculate Macaulay duration. Then we can find modified duration, which is the first derivative of Macaulay duration. We can also find convexity in that same spreadsheet. But if we're trying to approximate it, we do it this way. PV minus plus PV plus minus 2 times PV naught, divided by delta y squared times PV naught. Remember, we have to have convexity in there, so the square is how we get our convexity in there. So let's calculate convexity in the same process that we calculate Macaulay duration. Let us take our 5-year 3.2% semi at 100. We've seen how we've calculated Macaulay duration, a modified duration from here. Let's just focus on the last column, which is convexity of cash flows. We have to introduce convexity, so there's going to be a squared term somewhere. Whenever you see convexity in almost any kind of formulation, you know you're looking for a squared term. It is time to receipt. Basically, it's time squared. You take the time to receipt, and this is for the first cash flow. We'll calculate the 0.035. Take the 1 multiplied by the very next time period, which is 2. 1 times 2. So that's time times time, which is time squared. Multiply that by the weight. There is your numerator, and your denominator, because your numerator has a squared term, right? This is time, and this is time, so it's time squared. You're going to have a squared in the bottom. So we know to divide by 1.016. We've done that before, but this time we'll just square it. So let's just calculate this number over here, 0.7767. We will find what time period that is. That is cash flow 7. We'll multiply 7 times 8 to get time squared and multiplied by the weight. There is our numerator. And our denominator is 1 plus the cash flow yield, which is 1.6% squared. It's always 1 plus the cash flow yield squared, no matter what time to receipt it is. We're not done. You have to add it all up, and you will get 96.9558. How do we get to an annualized convexity? You can't just divide by 2, because remember, everything was squared to get there, right? So you'd have to divide by periods per year squared. Since we had 2 periods per year at semi-annual, you must divide this by 4 to get our annualized figure for convexity. A few things about convexity. Fixed rate bonds will have greater convexity the longer the time to maturity. So longer time to maturity bonds, longer duration bonds will have higher convexity. The lower the coupon and the lower the yield to maturity. Basically, anything that leads to higher modified duration for fixed rate bonds will lead to higher convexity. All right, another factor which increases the convexity of the bond is the dispersion of cash flows. So 2 bonds, same duration. The one with greater dispersion of cash flows will have the greater convexity. What does this mean? Let's say that you have 2 bonds with the same duration. One is a semi, one is a quarterly. Let's make it 3 bonds. One is a quarterly. Let's make it 4. One is an annual and one is a monthly. And let's say they all have the same duration. The monthly will have higher convexity than the quarterly, which will have higher convexity than the semi, which will have higher convexity than the annual bond. All right, let's put this to the test. Let's calculate the change in the price of a bond, accounting for both the linear and the second order effect. Let's take a 30-year, 4.625% annual coupon bond yielding 4.75. Right away, I know I got a discount bond, right? N is 30, payment 4.625, future value is 100. There's my interest rate factor. There's my present value. That's PV naught. We're going to increase the required yield by 5 basis points and decrease the required yield by 5 basis points. So 4.75 to 4.8 and 4.75 down to 4.7 and recalculate. These are already in our calculator. We don't have to enter them again. Once you enter in all 4, you hit compute PV, you'll get this. Just type in 4.8, enter it into the interest rate factor, then compute PV again. You don't have to enter all these all over again. Those are the 3 things we need. Well, actually 4 things, right? Our delta Y is 0.0005. We need that. We need PV naught, we need PV plus and PV minus. So approximate modified duration is 98.8065 is PV minus PV plus, which we have here, divided by 2 times the change in yield, multiplied by PV naught, 15.90636. What's our convexity, approximate convexity? PV minus plus PV plus minus 2 times PV naught over, remember now convexity, you're going to have to get a square in there somewhere. There's the yield squared times PV naught. 369.64. Let's drop interest rates 50 basis points. Right away, we should know that the change in the price of the bond will be positive, right? So the percentage change in the full price of the bond is, here is our linear approximation, negative modified duration times the change in yield. Here is our convexity adjustment, 1/2 times the annualized convexity multiplied by the change in yield squared. Notice that no matter what we put in here, a minus or a plus, because we're squaring it, the convexity term will always be positive. That's why it's always additive. It will always be positive. 0.0841 or 8.41%. Can we use convexity if we're using one of the dollar-based duration measures? In other words, we're looking at the dollar change in the price of the bond, not the percentage change. So recall, dollar duration or money duration was its modified duration multiplied by the full price of the bond. Well, we can get money convexity. I just write it out as DC, dollar convexity. So dollar duration, dollar convexity. It's just a shortcut I like to use rather than writing out money duration and money convexity all the time. You can choose whatever you like. For me, I recognize it. It's nice and simple. That does not mean that, if you don't see it written anywhere else, you say, well, what's going on here? It's just something I use. So dollar convexity is just your annual convexity times the full price of the bond. All you're doing is multiplying your statistic, which is a percentage change, by a dollar amount. That's it. And that'll give you the dollar duration or the dollar convexity. So the dollar change in the price of the bond would be your dollar duration times the change in yield plus 1/2 times your convexity statistic multiplied by the yield squared. It's just here our convexity statistic is a dollar convexity and our duration statistic is now a dollar duration. So using the previous example we did on the last screen, we got to a duration of 15.9, we got to a convexity of 369.6. Let's say the full price of the bond is 100 million. In using this, we know the percentage change in the price of the bond was 8.41%. So we should get to $8.41 million change using the dollar statistics instead of the percentage statistics. So there's our duration times the dollar. So there's dollar duration times the change in yield, which is exactly the first linear term. There's 1/2 times, there's our convexity, but now it's dollar convexity. Our convexity statistic multiplied by the full price of the bond times the change in yield squared. Actually, yeah, that's right. It was 50 basis points. I was going to say I'm missing a 0 in here because I thought it was 5. 50 basis points. I got that right. I got it right. There's your linear approximation. There is your convexity adjustment. There is the dollar value change in the full price of the bond. Finally, portfolio duration. What if we have a portfolio of a bunch of bonds with a whole bunch of different durations? We can calculate portfolio statistics the same way we calculated Macaulay duration, the weighted average time to receipt of aggregate cash flows. So what does that look like? Let's say we have a bond 5, 5, 5, and 105. And we have another bond that is, let's say, 2.5, 2.5, 2.5, 2.5, 2.5, 2.5, and 102.5. In a portfolio, it would be 7.5, 7.5, 7.5, 107.5, 2.5, 2.5, 2.5, and 102.5. Notice that you have weightings that don't put all of the weight on the last cash flow because you're going to have bonds that mature all across the spectrum. So you can calculate, you can add up all of the cash flows in one column and you can calculate what the portfolio's cash flow yield is and calculate it the same way you do with Macaulay duration. This is the theoretically correct way to do it. There is an approximation to do it. It's just use the weighted average of each bond. So you'll have the market value of bond A over the sum of all the market values times the duration of bond A plus the market value of bond B over the sum of all the market values times the duration of bond B. On and on you go. This is an approximation. This is the correct way. The flatter the yield curve is, the closer these two happen to be. Most portfolio managers will use the weighted average of each bond because it's easy to write an algorithm in your platform to get that done. It's much more difficult to do it based on portfolio cash flows.